On last Tuesday, we were in the middle of proving a certain results, which says the following. G, as usual, is a finite group. And rho I from G to GLVI are pairwise non-isomorphic, are the pairwise non-isomorphic irreducible representations of G. We know that there is only a finite number because they are the irreducible representation that occur in the regular representation. So for I, say 1, 2, T. And we will later see exactly what this number T is. Note that there is an alternative way of describing this, as I have repeated several times, as in the case of actions of groups on sets. You can describe representation in two ways, either in this way, or you can say that VI are the pairwise non-isomorphic simple modules, simple or irreducible modules for the group algebra. Okay, so it's the same thing, and we saw how to go from one to the other. But explicitly, we consider the direct sum of these representations, okay, which goes from G to the direct product of this GLV. Okay, so the representation is clear. It sends G to a tuple. Here you have rho 1 of G, and here you have rho T of G. Okay, but if you want to see it as modules, what is being said here as modules over the group algebra CG, in other words, okay, in other words, say the direct sum of these vector spaces, which are modules for CG, becomes a CG module via, so if you have an element here, so say a tuple of vectors, and here you have an element of the group algebra, it simply acts on all elements. And remember, whereas in this first representation with representations, we know that this is rho 1 of G and this is rho T of G. So the action here, so V1, just to have a mirror symmetry with this, you have an element here in the direct sum V1 plus Vt. What does this do to these tuples? It simply acts on each component with the relevant representation. Okay, so rho 1 of G acts on V1 and so on, rho T of G acts on Vt. Here we have lost trace of rho 1, rho T, but of course this action here is nothing else than the sum. This is sum over G, AG of V1, rho 1 of G. Okay, so it's written, these are written in the same way, but one means that when V1 is an element of vector space V1, the action is via rho 1. Okay, and so what's this, for instance, is the sum of Vt rho T of G. Okay, so the two are equivalent. And so we were recalling the universal property of the group algebra, and the universal property is the following. You have this map rho 1 rho T, that goes from G to GLV1 times GLVT. And of course, this is included in the end V1 times, or direct sum, it's the same, really. The direct product of this, because these are invertible matrices, and these are just all the matrices, okay? Or abstractly, these are all linear maps on V1, and these are the invertible ones, okay? But then G goes inside this, and then the universal property of the group algebra tells you that you have a morphism, phi, a morphism of algebras. Okay, from there to there, and the morphism is exactly the one we saw a moment ago, is the one that takes an element of the group algebra. The sum is always intended to be for little g in big G, goes to the, it has to go to a tuple of endomorphism, and so what's this? It's what we saw a moment ago. Okay, it's this. Okay, so this as you see, on each space Vi, this is an endomorphism. It's okay. It's what we saw earlier in the previous page. V1 goes to V1 on which this acts, and so on. Vt goes into Vt on which this acts. All the individual maps, Vi to Vi sum over Gg, are endomorphisms of this. Okay. Now, so we have these morphisms of algebras, and we know that the two algebras have the same dimension. Why? Because we know that the dimension of CG, this is always meant of course as the dimension over C, is the order of G, and we know that the dimension of that direct product or direct sum, it's really a matter of okay, this dimension is the sum of all the dimension, because what we have here, we have really block matrices, okay? This will be important in it. So here we have all matrices, here we have all matrices, and here we have all matrices, and zero elsewhere, okay? And so the dimension of this will be the sum of this dimension. This is a vector space, and the sum of this dimension, which is the dimension V1 square plus dimension, because, I mean, these are matrices of size, of this size. And what we have proved as a first consequence of the results we studied on characters, this is exactly the order of G, is the same. This we have proved by showing that the right regular representation is the sum of each character, which its dimension as a multiplicity. Okay, so this is an important result. This follows from characters. Okay, from characters and from the composition of the right regular representation. RRR stays for the right regular representation in terms of irreducible modules. The last lecture, the lecture of last Tuesday has been quite intense, so take this chance to review these results when we use them, okay? So this sum of squares of the dimensions of the irreducible modules, remember V1, Vt are the irreducible modules, pairwise non-isomorphic, gives you the order of G, okay? So the two dimensions are equal, okay? We have proved that the two dimensions are equal. If we prove that this morphism of algebras is injective, then the two will be isomorphic, okay? Because it's, the dimensions are the same. If it's injective, it's a matter of vector space that it's also surjective. So I want to prove, well, okay, it's called the R on the notes, but it doesn't matter. I intend to prove that phi is injective. And then, since the two algebras have the same dimension as vector spaces, it will be also surjective. This is this is absolutely a matter of vector spaces, and then an isomorphism of algebras. Okay, so my plan is to show that it's injective. And of course, how do you prove that such a thing is injective? It's enough to consider it as a linear map, because it's a morphism of algebra, in particular vector spaces. So we have to prove. Since phi is a morphism, to be proved, kernel of phi is equal to 0. Okay, this is the advantage of having a morphism, that you can reduce injectivity to proving that the kernel is 0. Good. How do you prove that? Well, let such an element, or the sum is always over G. I'm writing this, but then as usually I'm leaving this out in the following, and also in the previous slides. I mean, it's intended. Let this element be in the kernel of phi. So this means that this element goes to the 0 map. Okay. Okay. This element acts as 0 on these vector spaces. Okay. So this means phi of this is the 0 element in this product of endomorphic rings, endomorphic algebras, matrix algebras, if you prefer, if you take a basis. That is, what's the 0 here? Well, the 0 map is the map that sends every vector to 0. That means that vi sum over G equals 0 for all I from 1 to t, and all vi in vi. As we see, the advantage of using the group algebra notation, the module notation, is that we save the errors. It's easier. Good. So we have that. In other words, this element in the kernel, okay, there was an element in the kernel. So this element acts trivially as 0 on all the irreducible modules, reducible or simple. I'm using the two terms interchangeably. The reducible modules vi, okay? But now we recall a fact that I was evoking, that was mentioning on the previous slide. Consider the right regular representation of G on what it's really C of G, okay? Because C of the right regular representation means two things. Is the action on G on itself by right multiplication, and then you can extend it to a representation, a linear representation on a vector space which has as basis the element of G, okay? And this is, of course, a vector space with basis the elements of G, okay? Because the elements of the group algebra are exactly this. So the right regular representation, rho, should be goes from G to DGL, sorry, CG. What does it do? Well, it takes, let me think, okay, G. It takes an element G to a linear map. Is the map that takes the sum. The sum is always 2 over, let's say, H in G. To what we obtain if you multiply by G on the right. Okay. So the idea is that you have the right regular representation as actions. That it's a map that sends G. Let me write it here. G to the symmetric group to the set of maps from G to G, and this sends G to the map that sends H to HG. Okay, this is an action of G on itself, and then you extend it linearly to linear maps on CG because it's simply linearly. What does it mean linearly? That G acts in this way on each H, and so on the linear combination acts as the linear combination of the single actions. Okay. Now we have a representation from G here, and again the universal property of group algebras tells you that here you have CG. And you can extend this to, well, okay, to a mapping to the endomorphism of CG. So this is extension by linearity. There's linearity anywhere, everywhere. And what does it mean? Well, okay, so you have an element AGG, and this is sent to the map that sends this. To what? Well, to the sum over G in G, okay, of this. Well, okay, just a second. Just a second, yes, okay. No, okay, I have to change the notation. Sorry, this is a bad notation. Okay, so here I said, let me correct, this is something, let me do it in red. You can do it easily. Let's use B, because I have already used the A for the coefficients of this element. Okay, so that's a B now. And so this sends a BHH to what? To what you obtain by doing this. Well, no, just a second. This is H, so it goes to sum H in G, BH, HG. And if you look at what we have here, this is nothing else, since the coefficient commute, this is nothing else than the product as defined in the group algebra of the element, this element, by this element. Because the way you do a product of two elements of the group algebra, you multiply the group elements and then you distribute, okay? So if you do this, you obtain all products HG, and then you have this coefficient that they have regrouped. I mean, of course, AG and BH are complex numbers, so I can easily exchange it. And so this is nothing else than the product of this by this group element, by this element of the group algebra. So you see, the right regular representation of G on CG is also, so this is a right regular representation of algebras. Just compare this and this, okay? It's really the same thing, it's two different categories. Here you are in groups, so you take G to the right multiplication by G on G. Here you have algebras, so you take this element of the group algebra on to right multiplication by this element in the group algebra, okay? But it's an absolute analog, okay? This here groups and here algebra. You see, this takes G to the map that sends H to HG. This takes this element to the map that take an element in the group algebra and multiplies it on the right by this element. But you see the similarity. It's a same thing is two different categories. Good. So we have found this right regular representation of algebras, multiply on the right on CG. But we know that this representation and this one, okay, the latter representation we know this result I already quoted a couple of boards or slides ago. This decomposes as a sum of irreducible representation, a direct sum of irreducible representation. Say, let's speak of modules. A direct sum of irreducible, remember, reducible or simple for the modules, so they say modules. And how? Meaning that, okay, let's write it. So there's V1 several times. How many times? Dimension of V1. That's the content of this result that we found via characters. That if you take the right regular representation, so in this case, if you take CG as a CG module with multiplication on the right, this decomposes as V1, which appears dimension of V1 times, V2, which appears the dimension of V2 times, and so on, until you find Vt. These are the same modules that we had in the very first board, okay? So the right regular representation as a representation or as a modules decomposes. In this case, we are talking of modules of the group algebra, so we are talking of irreducible modules. So the modulus V1 appears the dimension of V1 times, the module V2 appears as the dimension of V2 times, and so on, okay? But now consider this element which was in the kernel of phi, okay? So this element, we have seen that acts trivially on every VI, okay? So this element acts trivially on every VI. And let's recall what this means. It means that it sends every element to 0, okay? So you apply this on any element, you take any I from 1 to t. You take any element in the vector space Vi, in the module Vi, you multiply by this element in the kernel and you get 0, okay? But then, I mean, this module CG is the direct sum of this. This means that this element acts trivially by right multiplication on CG. Because, let's come back, I'll be back in a second. So the action of CG on itself as endomorphic is by right multiplication, okay? Take an element of CG and multiply on the right by this, okay? But we have seen that this representation decomposes as sum of the irreducible ones with certain multiplicity, but this element acts trivially on each VI, and so it acts trivially by multiplication on CG. Is this possible? Well, of course it's possible, but note, in particular, you see, it acts trivially on each element of this form. Well, let's use the pointer. No, this one. On each element of this form. But among these elements, you have the identity. So choose as element, as this element here, choose 1, Okay, so it's the element in which all BH are 0, except when H is 1, the identity element of the group, and then B1 is 1. Okay, but then since this acts trivially by right multiplication on CG, it will follow that 1 multiplied by this is 0, because this multiplies to 0 every element here. But of course, this is this being the identity of the algebra in particular. This means that this element is 0. So what we found that if this element is in the kernel, then it's 0. Okay, we have proved that the kernel is 0. Okay, and we have used the fact that the right regular representation is faithful. There is an element in the kernel of this has to be 0. And since we knew that an element in the kernel of phi acts trivially on all these irreducible modules, it has to act trivially on here, but there is the identity here. So the only way for this to happen is if this element is 0. Good. So what we have found? We have found that there is there is an isomorphism of algebras. In particular, of vector spaces, from the group algebra to this direct product or sum. Okay? As I was telling one of you at the beginning of the lectures, there is a theory of semi-simple rings, non-commutative rings, due to Nathan Jacobson and then other people, in which this isomorphism comes from different consideration of rings. This is an elementary method due to Jean-Pierre Serre, a Fields medalist, whose lectures I'm following. Well, first, a remark on this, which is somewhat strange, because you see, this is a group algebra, okay? So it's something that depends very much on the group, okay? Because you start with the multiplication in the group and extend linearly. What's this object? Well, this is really the set of all matrices, as I was saying earlier, okay? Matrices, they have 0 in most of the places, and then there is a matrix here, A1, a matrix here, A2, and so on, until a matrix here, AT, okay? Where AI is simply a matrix in end VI. It's a direct sum, okay? Direct sum meaning that block matrices, these are block matrices, diagonal block matrices. So matrices that have only something on a block diagonal. And if you look at the sum and product of these two objects, if you multiply this by, okay, B1 plus or times is the same, okay, what you obtain, I'm writing plus or times because it's the same whether you do this, you obtain exactly. Okay, and zeros everywhere. Okay, it's how block matrices behave with respect to sum and multiplication. Okay, you sum and you multiply. Okay, so this means no matter if you take plus here, you take plus here. If you take times here, you take times here. So, and this is a curious fact because, in a sense, you have lost the group. Here you have just matrix rings. Okay, so for instance, one of the consequences that we, sorry, as we will see, is that if you take all abelian groups of a certain order, of order n, say, then we will see, then all the group algebras are isomorphic, because they will simply be isomorphic to simply the algebra of the ring of diagonal matrices, in which really these are 1 times 1. Okay, so the group algebra may take very different groups, but then gets you isomorphic algebra. As I said, we will see that when G is abelian of order n, for all abelian groups of order n, all these group algebras are isomorphic. Okay, so you lose some information by going from G to the group algebra. Good. So we have this isomorphism, and now we'll use this isomorphism to compute the number of irreducible representation, this T, okay, pairwise non-isomorphic, in terms of an invariant of G. We will use this to compute T, which is the number of pairwise non-isomorphic irreducible representations or irreducible modules in terms of a group theoretic invariant of G. What I mean by a group theoretic invariant means a number that can be computed from the group itself, okay, without speaking of appealing to representations, okay. So on the one side, on the one hand, you have the reducible representation. On the other side, you will find the number of irreducible representations. On the other hand, you will find a group theoretic invariant of G. Okay, so let's first consider the dimension. Okay, yes, okay, fine. Let's proceed to the next one. So we consider, first of all, we recall the fact that that is well known, of course. What's the dimension of no? Okay, what's the center of end V? Okay, V a vector, a finite dimensional vector space. What's the center? So, as usual, I write end V, but if you can think of matrices, what's the center? The center is given by all the matrices in end V, which commute with all matrices. And it's well known, and I have written it in the notes, that this is simply given by all diagonal matrices. These being vector spaces over the complex number, you get this. Well, I always, when I don't write anything of diagonal, these are meant to be zero. I write a big zero to clarify this. Okay, so sorry, I said diagonal, but I meant scalar matrices. There is diagonal matrices with the same value on the diagonal. Okay, and of course the dimension of this on C, I mean dimensions are always on V. On C, well, too many. No, it's correct. Dimension is 1. Okay, because this is nothing else than lambda times the identity matrix. So visibly a vector space of dimension 1. Okay, of course, this is called the center. Okay, elements which commute with everything else. These are sometimes also called homotheties because they expand the space uniformly in all directions. For instance, if lambda is 2, for instance, in the plane C squared, you are multiplying everything. Every vector becomes twice as long and so on. Good. So this means that the dimension, of course, it's quite easy since the operation. No, sorry, since the operations are by components here. Okay, by components means this, and this. It follows that the dimension of the center of this is nothing else that the direct product of all the centers. Okay. Okay. So what does it mean? That an element here will be of the form, so an element here, this is a belong to, will be something lambda 1, lambda 1, lambda 2, lambda 2, and so on, until lambda 2, lambda t, okay? Where the lambda I can be different. So an element in the center of nv1, an element in the center of nv2, which I did not write, an element in the center of nvt. In other words, the dimension of this center is T, the number of irreducible representation, or pairwise non-isomorphic. Let's say simply write the number of irreducible representations. But I mean pairwise non-isomorphic. Good. So let's exploit the fact that these two are isomorphic to see what's the dimension of the center of this. So we have to understand what's the dimension. Actually, what is the center of CG? Let me see whether sometimes I route. No, okay, I always write it like this, yes. Good. So what's the dimension of, what's the center? Well, the definition is exactly the same. So this will be the set of elements here, such that they commute with every other elements for all elements in CG. Okay. Well, let's write. Okay, let's close the bracket, the brace. Okay. So it's the same definition. It's the elements of CG which commute with every element. But it's immediate to see, since here you have elements of G and then coefficients, the coefficient commute. It's an algebra, so the coefficients by definition commute. That this is the same thing as the elements of the group algebra, which commute with every element of G. For all. Because, I mean, once you know that they commute with H, the coefficients commute, and then it's done. So let's see what this means. So this means, let me write it correctly. Okay, so this means that for all H, you have, let me write this the way I want this to be. Yes, you have that the sum of AGG equals to you multiply on the right by H inverse, okay? So you get the sum for G in G of AG, and then H, G, H inverse. So this is the conjugate, okay, by H inverse. But of course, this is not written in the same way because it's not written with respect to the same base. So let's do a change of basis, a change of summation index. So we take, well, okay, we take this to be G. I write it, sorry, I write it as a red G to avoid confusion. Okay, so what we get, that if red G equals this, then this means that G equals H red G. No, sorry. Okay, H inverse red G H. Okay, because I mean, if red G is equal to AG, HG H inverse, you multiply on the right by H, on the left by H inverse, you get this. So what we get here, you get that this equals A, and here you have H inverse H, and then in the middle a G, okay? And now you can compare elements to elements because you have the same summation variable. And so if an element is in the center, if and only if for all G and for all H, you have that AG equals to this, okay? So this is in the center, or I'm writing in blue, is in the center, is in, well, let's write it because it's short, right? If and only if for G and H in G, we have that the coefficient AG is equals to the coefficients of HG, H inverse. No, H inverse, well, okay, because I have reverted. Okay, but what's this element? This is a generic element in the conjugacy class of G. Remember, conjugacy take an element G. If you conjugate it by H, it takes it to this. In other words, this is in the center of CG, if and only if the AG is constant on the conjugacy classes of G, which, remember, which are the orbits of the action by conjugation or conjugacy of G on G. So as an action, so it has to send, well, H to a map, and the map is the map that takes G to G, H inverse H, okay? Conjugation. Good, but then if this is constant on the conjugacy classes, let C1, CS be the conjugacy classes. Okay, just a second. Yes, and then this element here, since the coefficient is constant on the conjugacy classes, I can write this element in the following form. Yes, and let's say that G1 is an element of this conjugacy class and GS is an element of this conjugacy class. Okay? No, I don't need this. But yes, well, okay, fine. So let's take first the first conjugacy class. Okay? So on this conjugacy class, this element AG is constant and its value is AG1. And then I have the sum over the conjugacy class, okay? Plus I take the second conjugacy class, the element here is constant. So if G2 is an element of the second conjugacy class, I can pull it out and I will have the sum for G in the second conjugacy class and so on, okay? So you see, we have seen that an element is in the center if and only if this coefficient is constant on the conjugacy class. That is, this element is a linear combination of the sums over conjugacy classes, okay? So this element here in the center is a linear combination of this. And since it's immediate to see that these are independent, what we have found that center of CG is the vector subspace of CG with basis given by, say, sum over C of G, where C are the conjugacy classes, CI. Of G, okay? And let's say it again, because we found that this coefficient is constant. And so when you go through one of these sums, okay, let's redo the argument. So when I sum over C1 the AG G, So I'm summing over C1. This coefficient is constant, okay? These are all equal to the value of this on one of the element in C1. And so this is a constant that you can pull it out, okay? Okay, where, as I said in the previous slide, G1 is an element in C1, okay? So what we have found, the dimension of the center of CG is equal to the number of conjugacy classes of G. Because it's immediate to see that these are linearly independent, because they have different G elements here. So every element is a linear combination of these elements. So what's the basis? A basis is given by the sums of the conjugacy classes, okay? Because of the isomorphism, I will explain this, repeat this at the beginning of tomorrow's lecture. We have found that the number of irreducible representation of pairwise non-isomorphic irreducible representations of G equals the number of the conjugacy classes of G. And tomorrow we'll see that this allows us to write immediately down the irreducible representations of abelian groups, finite abelian groups, and then we'll also start to see the irreducible representation of some small groups like the symmetric groups, a group of 3 elements, or A4, the alternating group of 4 letters. Good, that's all for today. Thanks, and see you tomorrow at 2:30.